Okay, perfect.
Okay, you can go.
Good evening, everybody. Welcome to the 10th MRI Web Meeting. We are very excited to celebrate our 10th meeting already with you guys. It seems like time has been flying and we still can't believe it's already the 10th. We have two special guests tonight. First is Nick Bolas and from Hallmark Veterinary Imaging. And tonight Nick will give us an introduction to fat suppression and physics. So we thought we'd start out slightly different because there's not really anatomy. We are very, very excited to have Nick with us. He's a genius and has taught me MRI physics, so I'm quite excited and forever grateful. And then we also have Christian Falzoni with us from the Small Molecule Diagnostic Center, who's presenting a case later on in the meeting. We will start, as I said, with the physics, and then Elsa is going to present cases, followed by me presenting a case, and then Swan presenting a case, and then Christian, and then we also finish off with Marco and the histopathology. One comment I would already like to make: tomorrow we are sending out our feedback form again, and it would be really, really helpful if you guys could fill that out, because we have a question at the end that we're trying to really answer, and so please fill out the feedback form. We would be very grateful. And with that, I'm going to hand over to Nick, or Marco as one is handing over to Nick, and then we can start with the physics session.
Okay, Nick, I'm going to give you the power. You have the power.
Okay, I shall take advantage of that power. Hit that button. Hit this button. So thank you very much indeed for inviting me. Can everybody hear me properly?
Yes.
Okay, thank you. So as Anna said, I'm
yes, thank you.
One of the founders of Hallmark. You'll know the company from our standing equine MRI and our pet vet companion animal MRI. Thank you very much for inviting me. Your topic is when muscles light up. Muscles, as with any other tissue, will basically light up when you get more signal than you're expecting to see. That's likely to come from either water or fat. It could be contrast agents or some other peculiar reason, but in general it's going to be water or fat. I'm not going to show you any images at all today. I'm just going to go through some of the physics of how you can distinguish between water and fat, because the ability to do so is one of the real advantages of MRI over other imaging modalities. You're doubtless familiar with the idea of the MRI signal coming from the spinning proton, the nucleus of a hydrogen atom, and I put that screen up, and probably I've lost half the audience already because you'll think, oh my goodness, physics, nuclei, spinning, that's scary stuff. But we're not really going to look at the nucleus. What's not that obvious from classic MR physics is that the nucleus is just a tiny little dot in the middle of an electron cloud. And if you look at it roughly to real scale on my screen, that dot in the middle is about 0.5 millimeter across. And the electron cloud surrounding just a single hydrogen atom would be about 30 meters away, so, you know, the other side of my house. And that surrounding electron cloud sort of insulates the nucleus from other surrounding magnetic influences, or to some degree creates its own magnetic influence. And those influences affect the signal in two ways. One is to provide an interaction with the nearby environment. So you get different electron clouds surrounding different protons, and the nearby that interaction in the nearby environment will affect the relaxation of the signal that you're looking at, and we use that in image contrast and stir and flare types of fat suppression. The other way that you can get the influencing, is from atoms which are bonded closely to each other within a molecule, and that tends to show up as an adjustment to the precise resonant frequency of the signal. In the context of molecules, it tends to be called chemical shift rather than resonant frequency, but it's the same effect, and that is used for fat saturation methods of distinguishing between fat and water. So I'm going to look at those two. Again, here's a classic sort of diagram that you're likely to have come across, where you consider a a spinning nucleus in the ground state, in its resting magnetic state. You put on a pulse of electromagnetic radiation and you promote it up to a higher energy state by turning the spin upside down. And then at some point later, that higher energy state will fall back down again to the ground state, and in doing so will send out a radio signal, and that radio signal is the origin of what we make an MR image out of. And if you've been taught that and you remember it, congratulations, because that's correct. If you've also been taught and you also remember that this drop in energy state and irradiation is the cause of T1 relaxation, then I'm afraid that's not correct. Yes, that is a mechanism, but because the energy difference between this high energy state and low energy state is so small, the spontaneous rate at which the nuclei would change from one to the other and fall and lose energy is very, very slow. In sort of optical spectroscopy, that's real and that's what happens. But in MR, that would take tens of thousands of years to lose the energy that you put in from a pulse. And in fact, relaxation occurs by a different mechanism entirely, and that is by interaction with fluctuations in the local magnetic field caused by nearby other nuclei, molecules, gadolinium, bits of iron, or whatever is floating around magnetically influencing the environment. If those nearby influences are in a solid, rigid structure, crystalline structure of some sort, they form what could be described as a lattice, and you'll probably have come across the term spin lattice relaxation for T1 type relaxation, because in the early 1950s when they were investigating this effect, it was in crystals that they worked out what the mechanism is. In a gas, nearby molecules are not nearby enough, and they tend to have so little influence that 2 ones in a gas can be seconds long. But in biological samples, we're tending to look at the liquid or very nearly liquid state. And atoms of molecules are going to be bouncing around, tumbling over with random Brownian type motions. Now, if those motions are just at the right sort of speed to produce magnetic fluctuations just at the Larmor frequency, the same frequency as you would have applied your RF pulse and the same frequency as you would try and observe your signal, then those random magnetic fluctuations are going to cause transitions in the nuclear energy state, and are going to cause those excited nuclei to drop back into their ground state, lose their energy, and that is the mechanism which causes T1 relaxation. But as I described there, it's a bit of a Goldilocks effect. It only really happens when the magnetic fluctuations are at just the right frequency. If the surrounding environment is vibrating too fast, then there's not much energy at the Larmor frequency, so you don't get much relaxation. And if it's vibrating too slowly, then you don't get much relaxation. What counts as too fast or too slow depends on the rigidity of what you're looking at. It depends on the temperature of what you're looking at, and because it depends on the Larmor frequency, of course, it depends on the field strength as well. So if you look at a water molecule, water molecules are very small, and you can consider here just a visual image of what water molecules might look like. Very rapid, buzzing around all over the place, so they tend to have very fast interactions. They don't really cause T1 relaxation very effectively. Fat molecules, on the other hand, are structured very much bigger molecules. They look like this, or they look like this, and you can sort of mentally imagine them as being much slower, lazier molecules. Here's some tadpoles in a fish tank, and so they will interact with their environment at a different speed. So if you look at the end result of that, and you consider a ridiculously simplified MR experiment, you've got your magnetization sitting here, you put on a pulse, and you get that magnetization into an excited state. You've moved it away from its resting state, and then you're waiting for it to come back again, and it gets back up to a certain height, If it's relaxing quickly, it gets up to that height quickly. You can observe it at this point, put on another pulse, observe it again, put on another pulse, observe it again. So this blue line, which is relaxing quickly, is giving us a fairly strong signal, because every time we put on a pulse, it's quite a high level. So something which relaxes fast, like fat, will give us a lot of signal in a T1 weighted type image. Water, on the other hand, relaxes more slowly, so it's never really got up there before you hit it back down again, and so you're not getting very much signal. So your first primary way of distinguishing between fat and water is your basic T1 weighted image. But that's not very sensitive. It gives you low contrast. It gives you even lower contrast if you use the wrong TR or different flip angles. So whilst it can be useful for imaging quickly or for imaging with contrast, you really need to enhance that to get good fat suppression. And the stir image is the fundamental way where you use T1 to enhance the contrast. Instead of putting on a 90-degree pulse, you put on a 180-degree pulse. You invert your magnetization, at which point it starts to recover. And you can see after a certain length of time, the fat, which is recovering quickly, will get to our sort of initial zero magnetization state. You've gone upside down, got back halfway, and at exactly this point, you've got no signal from fat, whilst water, which is recovering more slowly, will still give you a signal. So the fundamental stir sequence, put on a 180-degree pulse, wait for a certain length of time, and then at this point, you observe with your imaging pulses. The advantages of stir is that because you can null the fat very precisely, you get a very high contrast, good fat suppression. And also it works well at low field because there's the T1 difference between fat and water decreases at higher field and it is more enhanced at low field. But there are many disadvantages of stir. It's slow because it needs a long T1 to recover before you can do it again. It's got a poor signal to noise because you've thrown away some of your water signal before whilst you're throwing away the fat signal. The inversion time matters. It needs to be calibrated. It will vary according to temperature and breed and species and even pathology. And so there is a risk that you will sort of calibrate your stir to suppress what you think is the fat, but actually you're suppressing real pathology. It works less well at high field, so if you get up to 3 Tesla, for example, it really doesn't work well at all. And it can be susceptible to a number of artifacts, including flow artifacts, because inflowing blood never sees the inversion pulse in the first place, so it's going to be maximally sensitive to your observation pulse. So stir has its advantages. There's another variation, which is flare, which is fluid suppressed. So at that point, you wait for the water to null, and you can see your fat. And this can be used for water suppression, fat observation. Because you're waiting such a long time for the inversion, it's even slower than stir. I know I'm over my time, so I'm going to try and keep the rest of this as brief as possible, but move on to chemical shift methods. This axis, the horizontal axis on this graph, represents frequency, the Larmor frequency, the resonant frequency, but on a very, very fine scale, and it's expressed in parts per million. You zoom in very, very closely to the signal which is generating your brightness, so bright would be up in this direction, dark down in this direction. You see a huge peak from water, and not quite at the same frequency. Hydrogen atoms which are connected to carbon and shielded slightly differently by their surrounding electrons, giving a slightly different magnetic field, slightly different resonant frequency. But that gives us the opportunity to apply the radio frequency signal, pulse, whatever, just to the fat and missing the water. So suppressing the fat out, so you get not much signal from the fat because you've pre-irradiated it whilst still observing your water signal. There are various technical difficulties with doing that. It's actually quite difficult to saturate a signal, particularly if you're trying to do it in a single slice whilst not affecting the signal from nearby slices. So it tends to be not actually technically a saturation, but a 90-degree pulse followed by a homospoil, followed by a gradient pulse, which sort of smears out a little bit like a T2 star, smearing out your signals quickly. There's also variations on a theme where you can invert it, or variations where you can do spatially selected saturation pulses. But fundamentally, what you're relying on is a very precise difference between frequencies, and that requires a good magnetic field homogeneity, and it requires a strong magnet to separate the water peak from the fat peak. If you're using low field, the water peak and the fat peak are so close to each other and relatively speaking so broad that when you put on your irradiation pulse, you actually hit the edge of the water peak. And because the water molecules radiating here are rapidly diffusing and rapidly reacting with all the ones out here as well, even if you try to irradiate the fat peak, you end up suppressing all your water as well.